Let's talk about tool calling in AI agents. Today we're going to cover this topic in 3 steps. On your screen, you can see all 3 sections laid out. Step 1 covers the core concepts and theory. Step 2 shows actual code examples. And step 3, which ties everything together with the real world architecture. So let's start with step 1. So why does tool calling matter in AI agents? Here's a fundamental limitation. Large language models on their own can only do one thing. They take the text in and they produce text out. That's it. No side effects, no real world actions. They cannot check your calendar, they cannot query a database by themselves, and they cannot send an email by themselves as well. Tool calling actually changes that completely. When you give an AI agent access to tools, it can now reason about a problem, take an action, observe the result, and then iterate until the task is completed. This is what separates a chatbot from an actual autonomous AI agent. Now let's understand how tool calling actually works under the hood. There are two layers working together here. The first layer is the language model itself. When you provide tool definitions to the model, it can output structured JSON indicating which function it wants to call and with what arguments. The model is essentially saying that, okay, I need to call this function with these inputs. The second layer is the agent framework. This is the orchestration layer that actually executes the function, captures the results, and feeds it back to the model for further reasoning. This loop continues until the task is actually completed. So the model decides what to call based on the user intent and available tool schemas. Then the Microsoft Agent Framework will handle how to call it and how to manage the entire conversation loop. And then it results the flow back into the context so the model can reason about the outputs before producing a final answer. Now let's cover the tool type 1, which is function tools. This is the first type of tool that you should know about when you're trying to build AI agents. These are custom functions that you write and you want the agent to invoke them when needed. Any method in your code bases can actually become a tool simply by passing it to the agent's tool parameter. So here's what happens behind the scenes. The framework automatically generates the JSON schema for your type annotations and descriptions. Then the language model sees this schema and decide when to call your function based on user intent. Then the results actually get injected back into the conversation context for reasoning. The key implementation detail here is that the descriptions matters pretty importantly. So for example, in Python, you should use the AI underscore function decorator along with type hints and pedantic field annotations. In .NET, you should use the AI function factory dot create method with description attributes on your methods and parameters. The model uses these descriptions to decide which tool to select, so good descriptions are very important for accurate tool selection. Now, the second type is MCP Tools, which stands for Model Context Protocol. MCP connects your agents to external servers through a standardized discovery and invocation protocol. In Python, you should use the MCP's stdio tool class to connect to a local MCP servers via standard input-output. In .NET, you should use the MCP client factory create async with stdio client transport. So one important security consideration here is that your credentials stay local and they're never sent to the language model. Only tool results flow back. The protocol can operate over stdio for local processes, HTTP with server send events for remote servers, or WebSocket connections. So now, when should you use MCP? First, when you're accessing third-party services that already have MCP servers available, like GitHub, file system operations, or databases. Second, when you're actually building reusable tool servers for your own organization. And third, when you need standardized tool discovery across multiple agents or even different frameworks. Now, the third type of tool is hosted tools, and these run on Azure AI Foundry managed infrastructure. These are three main hosted tools that you should know about. The first is hosted web search tool, which gives you real-time web search with location awareness. The second is hosted code interpreter tool, which provides a sandbox Python execution environment. And the third is hosted file search tool, which enables vector search over uploaded documents. The advantage here is that there is zero infrastructure management on these tools scale automatically by the Microsoft Agent Framework. Now the fourth type of tool is the using agent itself as a tool. This enables hierarchical composition. In Python, you call the as underscore tool method or any agent to wrap it as a function tool. In .NET, you use the as AI function method. So what does this allow is that a parent agent to treat a child agent entire reasoning capability as a single tool call. And here's the important point. The parent agent only sees the child's final answer, not the internal reasoning. This saves the significant tokens and keeps your token context window pretty small and clean. So when should you compose AI agents this way? First, when your toolset becomes pretty large enough that the selection quality starts degrading. Second, when you have complex reasoning that benefits from specialist delegation. And third, when you need clear separation of concerns between different domains. The next concept I want to cover is the human in the loop approval. You can mark sensitive functions for human review before execution. In Python, you add the approval mode parameter set to always require in your AI function decorator. In .NET, you can wrap your function with approval required AI function decorator. So when the agent wants to call an approval required function, the run pauses and then returns a function approval request or content object to your calling code. Your application then gets human approval, creates a response, and then resumes the agent. This pattern is pretty important for any action with real world consequences like processing payments, deleting data, or making external API calls that cannot be undone. So now let's move to step 2 and let's look at actual code examples. In this example, we're creating two tools. The first function, getWeather, takes a location parameter and returns weather information. The second function, getStockPrice, takes a stock symbol and returns pricing data. Both functions use the AI function decorator with clear descriptions and both use annotated types with pedantic field descriptions for the parameters. Then we create an agent using Azure OpenAI Chat Client with our credential and we pass both the functions to the tools parameter. When we call agent.run with a query, let's say, what's the weather in Seattle and Microsoft stock price, the agent automatically analyzes the user intent, selects both tools, executes them, and then synthesizes the results into a natural response. The framework can even execute independent tools in parallel when appropriate. Now let's look at the MCP integration code example. This pattern here uses Python's async context managers. We create an MCP stdio tool with name, command, and arguments. In this example, we are connecting to the GitHub MCP server using npx. The critical detail here is that the async is async with syntax. So for example, you need to keep the MCP connection alive for the entire duration of the agent run. If you exit that context manager too early, your agent will lose the connection to the MCP server. Inside that context, we create a chat agent and pass MCP underscore server directly to the tools parameter when we call run. The framework automatically discovers all the available tools from that MCP server. Now let me quickly summarize the tool registration patterns that you should know. You can pass functions directly to the tools parameter and the framework uses the docstring as a description. You can use the AI function decorator for explicit control over name and description. You can pass an MCP server directly as tools. And you can wrap specialist agents using the AS Code tool method. You can also use hosted tools like hosted web search tool and hosted core interpreter tool, and you can add approval requirements using the approval mode parameter. Now, let's see how all of this comes together in a real world architecture in the next step, step 3. Here's an enterprise customer service platform that handles thousands of daily conversations across supports, sales, and technical queries. The architecture follows a router pattern. Input comes from multiple channels, including web chat, mobile apps, and partner APIs. All of these feed into a single orchestration agent. The orchestrator's job is to classify intent and route to the appropriate specialist. For billing and order inquiries, it routes to the support agent, which has tools like create ticket, get order status, and process refund. For pricing and purchase questions, it routes to the sales agent with tools like check inventory, apply discount, and create quote. For how-to questions and error troubleshooting, it routes to the technical agent with tools like search docs and run diagnostics and escalate. So each specialist connects to appropriate tool infrastructure. Function tools handle custom business logic hitting the CRM and ticketing systems. MCP servers handle integration with knowledge bases, GitHub, Slack, and databases. And hosted tools provide web search and code execution when needed. Now let me walk you through how a typical request flows through the system. A user and sends a message like check my order and apply loyalty discount. And then the orchestration passes this to the language model along with all available tool schemas. Then the model analyzes intent and returns tools calls like, for example, get order status and apply discount. And here where it gets interesting. These two tools are independent, so the framework executes them in parallel. One tool queries the order database and returns order 1234, let's say ship Tuesday, and the other tool updates the CRM and returns the 15% loyalty discount applied. Then both these results flow back to the model along with the conversation context. Then the model synthesizes a natural response. For example, your order 1234 ships Tuesday, and I have also applied a 15% loyalty discount. Now let me leave you with some key patterns for production deployments. First is regarding tool limits. When your toolset exceeds what a single agent can reliably select from, you should split into your specialist agents composed as a via as underscore tool method. There is no hard limit, but selection quality typically degrades when you have too many overlapping tools. Second is regarding stateful operations. If you have function tools with instant state like a booking service that tracks reservations, or that state which must be persist to external storage, any load balance deployment, in-memory state breaks when requests hit different instances, so you have to be careful for that. Third, you should use approval required AI function, for example, any high risk operations. So this gives you human confirmation gates before irreversible actions. Fourth, you should enable open telemetry tracing. So for example, you need visibility into tool selection and execution across your entire agent chain for debugging production issues. So make sure you actually enable the open telemetry tracing as well. And for fifth, for credentials, you should use the managed identity credential in production environments. Azure CLI credentials should only be used for local development. So to summarize now, that was tool calling in AI agents using the Microsoft Agent Framework. We have covered the concepts in step 1, then actual code example in step 2, and walk through production architecture in step 3. The key takeaway is this: the tool calling is what transforms a language model from a text generator into an autonomous agent that can then reason, act, and complete real world tasks. You should start with function tools for your core business logic, add MCP tools for external integrations, use hosted tools to avoid infrastructure overhead, and compose agents when complexity demands it.